Okay, in chapter 7.5, we have discussed the operation of single star matching, dual star matching, and the third technique we will learn today is transformation across discontinuity. So the scenario is shown in the plot. So you have two sections. One to the left, the characteristic admittance 1 sub 01, and to the right, the line characteristics admittance y sub 02. So characteristic admittance of the two lines are not necessarily the same. So you can have two lines of different admittance or different impedance. And in the middle, in the interface of the two lines is a shunt element. And again, it is not necessarily a shunt element. It can be a series element as well. But anyway, you have discontinuity in not only in the line admittance but also the interface. So you have an extra component on the interface. So today we will check what happens and what can be done in terms of Smith chart operation. So let's take a few extreme cases. The first case is the YD, the admittance of the shunt element is in fact an open element, which is kind of trivial, which says that, well, you don't connect anything at that point. So open represents that you don't have anything connected at that interface. So as a result, the admittance equals to 0 because nothing goes through this component. So it's simply a connection of two transmission line. So assuming that the characteristic admittance are different, one y sub 01 and y sub 02. So we are interested in see what is the normalized admittance looking from here to the right. So of course here you see lowercase y2. That's indicates the normalized admittance looking at the y of this dashed line to the right. So of course, to do the normalization, you should divide y2 with respect to y sub 02. The admittance at this position looking to the right by dividing its characteristic admittance, and y1, that is the admittance, the normalized admittance looking from the left of this dashed line to the right. All right, so because the line admittance is y sub 01, so you do this for the normalization. Of course, there is a problem. As you can see here, they are both normalized admittance. However, they are normalized to different line characteristic admittance. They are normalized to different values. So here is an calculation that helps you to transform the normalized admittance to find out the normalized admittance from this position, from the left of this dashed line. So we know that the actual admittance with this shunt configuration is the sum of the admittance looking to the transmission line and looking to the shunt components. So it's y1 equals to y2 plus yd. And of course, we would like to express the normalized admittance looking from this position, that is y1. So by definition, that should be y1 divided by y sub 01. And if you apply the same denominator to the right of the equation, you have this result. And however, they are different from the definition of Y2 and YD, which should be determined in terms of the characteristic admittance of the second line. So we have this modification by putting Y sub 02 to the top of the denominator Yeah. So the ratio of Y sub 02 over Y sub 01 is the ratio A. So that is the ratio of the characteristic admittance of the two lines. So this can help to solve the problem in representing the normalized admittance at the two lines. Okay, so beware. You should be aware of the difference over here. And if we continue this representation, we can further replace the normalized admittance lowercase y1 and lowercase y2 with the reflection coefficient. So here is the y1 expressed in terms of the reflection coefficient gamma 1, and here's the normalized admittance of y2 represented with reflection coefficient gamma 2. Okay, and this by taking into account the fact the ratio A, you have this representation. Of course, you don't need to memorize this equation. You just need to know the significance of this equation. This equation 7.61 is of the form of the so-called bilinear transformation. So here you can see the name bilinear 就是双 bi 是双嘛，linear 是线性的嘛，转换 transformation 转换嘛，所以它这边指的是一个1对1的转换关系，也就是前面两页你看到的是我们在一个这叫什么？不同的特征阻抗或者特征导纳的传输线连在一起的时候，因为我们习惯用所谓的正规化导纳或正规化阻抗来代表，但它其实在定义上面是两边并不是一致的因为他们是对于各自的特征导纳来去做相除，所以这边给你一个关系式当然这个东西不需要背啦，就稍微有个印象啦。跟关系式的话，就是给你一个额外的这一个参数 A 那这个 A 就称之为特征导纳的这个比例值这样方便你来去表示那对于这种两个不同特征阻抗或特征导纳所连接的那个传输线，它们的反射系数，也就是在这个不连续的前后的反射系数gamma 2跟 gamma 1其实是可以转换的那它的特性就是说它是一个1对1的转换关系1对1的转换关系，所以这个倒是不用担心，就是说你去用这一个关系式套上去，其实就可以当你从不同的特征阻抗或特征导纳的传输线在走到不同的传输线的时候，它的反射系数它的那个输入阻抗或者输入导纳都是可以做转换的就是利用这样子的关系式来去做转换就好了那重点在于它是一个1对1的对应关系 OK 那 so consequently low C of gamma 2指的是在 gamma 2它的我们知道在那个传输线上面，在 Smith chart 上面传输线的轨迹会长成一个圆嘛，对不对长成一个圆，那个圆我们称之为什么 constant SWR circle也就是在那个圆上转的时候，因为你的传输线只要没有额外的耗损的话，它的反射系数的大小是固定的，只是它的反射系数的角度它的 angle the face of the reflection coefficient may vary at a different position on the transmission line. Nevertheless, the magnitude of the reflection coefficient remains as a constant on this constant SWR circle. However, if you in the following example you will see that by changing by connecting an extra element in shunt or series configuration, you can change the locus of the reflection coefficient. And so in the following example, we will demonstrate that it's possible by connecting a shunt element to improve the reflection coefficient, to improve the standing wave ratio of the transmission line, of the input impedance. Okay, so in the previous slides, it just show you or just tell you that the constant SWR circle on one Smith chart can be mapped into another circle on the Smith chart. And of course, there are some difference. So today, in the following example, we will see the difference between the two circles between the in this transformation technique. All right, and so here are some description about drawing the circle on the Smith chart, but I guess we will come back to this description later before we get into the problem, after we get into the problem. All right, so because the transmission line itself is the so-called passive component, so the bilinear transformation relationship, that is the one-to-one transformation relationship, is valid for any linear, passive, and bilateral. 这边 bilateral 这个字知道什么意思？双向的双边的或双向的称之为 bilateral 那个对应的一个字叫做 unilateral。是吗？是 unilateral 吗？对 ，unilateral 吧，或者是多面向的 multilateral。所以有人在骂说川普的那个政策就是 unilateral 就是单边的单边主义Alright, so most passive components, microwave components, satisfy the condition of linear, passive, and bilateral. Okay. So let's get into the problem. All right. So example 7.7 shows the application of the Smith chart to transform across a discontinuity. All right. So here in this example, as shown in the bottom of the slide, you have a termination of admittance. YR equals to what? Equals to 0.6 plus J.8. And so if you draw the Smith chart, where's the position of 0.6 plus J.8? 在哪里 ？0.6 加 0.8 J， 0.3、0.4、0.8， 这边是1。大概这里吧。Okay. So that is YR. Okay. What next? Alright, so here's the termination. We should write in lowercase r. And what you should do next is what? Is draw the constant SWR circle. So this is the locus of the reflection coefficient. By moving to the different position on the transmission line. Okay? Questions? How long does it take to rotate one full circle? Half a wavelength, 0.5, right? What happened to the value at this point? Well, the admittance here happens to be the inverse of the admittance here, right? If you have occupy opposite position on the same constant SWR circle. The product of their impedance or the product of their admittance should equals to what? Equals to 1. Okay? Alright. So we are moving. So the reflection coefficient locus moving on the transmission line shall form the constant SWR circle. Say at a certain position, you connect here in shunt with what? With susceptance, with reactive components. That is, the impedance or the susceptance is the impedance or the admittance is pure imaginary. Okay, so here the susceptance here is the admittance here is JB equals to J times 0.8. So what is the purpose of connecting this component? Well, let's take a look at the answer first, okay, to kind of a sneak preview, okay? Well, this slide shows you the purpose, the objective of connecting shunt element on the transmission line. Well, the purpose, the objective is to minimize the standing wave ratio. We are not aimed to achieve perfect matching as we have done on last Friday. Okay? On last Friday, we have demonstrated that you can do perfect matching by using the single stop matching or double stop matching technique. However, you should know that the single stop or double stop matching technique, for those techniques, even though you can achieve perfect matching, but it's only valid for one single frequency. In reality, in the design of radio frequency RF circuits for communication systems, in general, we like to achieve an acceptable matching condition for sufficiently broad bandwidth. 所以在实物上面来讲，虽然我们之前上礼拜五介绍的那个 single stop 或 double stop matching， 它可以做到完美的 matching 但是那个完美 matching 其实只在特定的频率上是有效的。只要你的频率偏掉，离开那个匹配的频率之后，它的反射系数就会上来，就会变大所以在实物上，有的时候我们并没有要追求所谓的完美的 matching 所以在实物上更常看到的一个状况是说，我希望在一个够大的频段都能够有可接受的匹配值，可接受的反射系数，只要它们够小就好，没有必要没有说一定要到0。那这个 example 其实就是 demo 这一个目标啦我想这一个 example 的目的其实就是要实现这件事情所以我们来看一下它是怎么做的所以在这个例子里头，你看到它并联了一个电钠 0.8J 的电钠，但它没有跟你讲要并在哪里，所以怎么办呢？我们就在 Smith chart 上面来去画出，当你把这一个 0.8J 的电钠并联上去之后，它可能存在的 locus 它在 Smith chart 上面的那个轨迹会长什么样子？从它的轨迹呢，我们再去选一个最佳的位置所以我们来看一下所以这一题你其实不是在教操作啦，其实是要教你说我们要了解的是为什么这样做它的动机是什么，它的目的是什么，好不好 ？Alright, so the red circle on the slide shows the constant SWR circle by moving the Y2 position to different location on the transmission line. So the red circle are are the locus of moving the observation points on the transmission line for half a wavelength. No, so it forms a complete circle. And the connection, the shunt element, can be connected at any point on this red circle. And we would like to know at which place, once you place this shunt element, the reflection coefficient magnitude can be minimized. All right. So what we know is this element provides a susceptance of positive 0.8 J, right? So, for example, if you are located at point C, now that at point C, the admittance is what? The admittance is 0.6 minus J 0.8. So if you connect the shunt susceptance at this position, it will give you a positive J of 0.8. Then the sum of the two equals to 0.6, which means it will move to this position F. Why? Because F is the intersection of the G equals 0.6 circle and the horizontal axis. Horizontal axis means there's no susceptance. The imaginary part of the susceptance is 0. So if you connected this shunt element at a position C, the admittance becomes 0.6, 0.6 only. So it will move from this point to point F, okay? If you connect the shunt element right at the very beginning of the termination here, what is the result? If you connect at point A, now that the admittance of point S is what? Is 0.6 plus J 0.8. And you add another J of 0.8. You will end up at the position D, which is what? G equals to 0.6 and B equals to 1.6. So if you connect it over here, YD equals to 0.6 plus J 0.8 plus J 0.8, and you end up with 0.6 plus J 1.6。对 ，D 在这里。Okay, so we have already drawn 2 points, and as the principle of drawing a circle is you need to have 3 points. Okay, once you have 3 points of the circle, then you can draw the circle completely. So what else? Which place else? Okay. Well, in the textbook it shows position B. Well, why? For position B. OK. 为什么要选 B 这一点？选 C 这一点是好操作啦。为什么？因为 C 点本身的那个导纳值是 0.6 减 0.8 J， 那它要加 0.8 J 嘛，所以那个 0.8 J 抵消掉之后，它就跑到10步走上去。B 点这一点也是同样的道理，因为它的 B 点的虚部你有没有了解的？有没有注意到 B 点的虚部也是负 0.8， 所以你在 B 点并联那一个电纳的时候呢，也会把它的虚部抵消，所以它会从 B 点跑到 E 点，E 点是纯实数嘛，对不对？所以你只要沿着在 Smith chart 上面，你只要沿着 B 点所在的那一个实数圈圈 constant G circle 往上移动 0.8， 事实上也就是把那个虚部抵消掉，它就跑到 E 点了。OK， 好。So if you choose position B and the convenient thing is the imaginary part can be cancelled. So you move to the what? On the horizontal axis. Alright, so we have 3 dots. 1, 2, 3. And you need to draw a circle that is passing through these 3 points. How to do that? Well, let's go back to your junior high school geometry, right? 怎么画？叫什么？中垂线还是什么？中央平分线。所以还是要用圆规啦，用圆规比较方便一点。这边画一下，画一下，画一下，画一下，那就画出一条中垂线了。用这2点为准。这2点为准呢，教一下，教一下，教一下，教一下，画出它的中垂线。所以这2条中垂线的交点就是你的新的圆的圆心，然后沿着新的圆的圆心跟已知的半径画出这个圆 ，OK， 大概是这样子。那我们在课本的 slide 上面也有这个轨迹。Let's check. So how to do that? Well, so in fact we deliberately or arbitrarily, actually you can do that arbitrarily, but as you can see in the previous slide, we kind of deliberately choose 3 points to find a shunt admittance result which are convenient to calculate. All right, so you have from C to F, B to E, and A to D. So you have 3 points. And the 3 points, the blue circle can be drawn by these techniques, all right? Okay, so we have C moves to A, B moves to F, E, and A moves to D, okay? By adding 0.6 of susceptance to their original admittance, okay? So as you can see, for the 3 points, all the 3 new points have 0.8 more susceptance than its original position. Okay, so you have D, E, and F. The one mass is use your ruler and compass to draw these 2 lines. 课本有给名字吗？没有国中的几何操作了OK， 好吧，所以你会看到先画连接线，然后再画中垂线中间平分线、中央平分线，然后找出它们的交点所以这个就是你新的圆的交点，然后这个圆到 D、E、F 的长度都是相同的，所以你可以用圆规用这个当半径绕出一个圈圈，得到这个蓝色圈圈所以这个是并联之后所可能得到的所有的位置所形成的一个轨迹并不是说你并联之后会得到这个蓝色圈圈，而是这个蓝色圈圈告诉你的是你在原来的红色圈圈，也就是 A、B、C 所转出来的 constant SWR circle 上面去并联 0.8J 的这一个电钠，它的所有可能位置、所有可能位置的集合是这一个蓝色圈圈。那现在的问题是，我要转到蓝色圈圈的哪里？还记得我们刚刚讲这一个操作的目的是什么？我们希望借由并联 0.8J 这一个动作，让它的 SWR 值能够减少。换句话说，也就是要让它的 reflection coefficient gamma 的绝对值最小。The purpose of this shunt susceptance operation is to minimize the magnitude of the reflection coefficient, is to minimize the standing wave ratio, so that a better matching can be achieved with this approach. So looking at the blue circle, where has the minimum SWR ratio or the minimum value of the reflection coefficient magnitude? 在那个蓝圈圈里头，你想想看，假如那个低点好了，那个低点是好点还是坏点？不好嘛，对不对？它很靠外面嘛，所以它的 SWR 值很高，对不对？那 F 点呢？E 点呢？E 点好一点，对不对？它离那个圆心的那个绝对距离是不是比较近了？至少比那个 B 点近得多嘛，对不对？所以你假如在 B 点并联，它转到 E 点之后，它的其实E 点的问题是什么？有改善没改善多少啦？因为你假如从并联之后进到 E 点，然后接下来它还是在这里绕一个圆圈圈呢。那这个半径没有缩小多少，对不对？你假如再到 D 点，然后传输线走下去的话呢，它会走一个更大的圈圈，对不对？那假如是 C 点进去的话 ，C 点照到 F 点，F 点呢让它继续转圈圈呢，又比较好，比较靠近圆心了。但最好的点是哪点？最好的点是 H 点啊。H 点加了 0.8J 之后，它跑到 G 点了。Shunt component 连到 H 点之后，它会跑到它的那个 admittance 变成 G 这个位置，然后呢再接传输线，它就在这一个新的位置上面绕圈圈。因为这一个点的那个 reflection coefficient gamma 的 magnitude 是在这个蓝色圈圈里头最小的所以这一个 G 点或者说这个 H 点会是最好的位置，可以吗？所以从蓝色的轨迹画出来之后，你就可以帮助你判断你这一个并联的元件要接在哪里，它可以让伽马的绝对值，或者是说，其实这两个是一样的事情啦，或者说 SWR 值这两个其实是一样的事情，能够最小，也就是匹配最好，驻波的成分最少So by connecting the shunt components of point A at the position H, you will move to the new position at the position G, and then if you connect another transmission line at the position G, the magnitude of the reflection coefficient is merely standing wave ratio at this circle is merely 1.35, which is relatively good in terms of standing wave ratio. Okay. All right. So again, as I already demonstrated, that to draw the blue circle, you need to find 3 positions, find a resultant admittance, such as from C to F, B to E, and A to D. With D, E, F at hand, 3 points, you can draw the circle, and the circle represents all the possible results of connecting the shunt susceptors. And the red circles indicate that at this position, that is, connecting the point A, J, at the position H, it will move to G, and the resulting reflection coefficient magnitude and the resulting standing wave ratio can be minimized to merely 1.35. Okay? So that's the kind of the optimal position. All right. Before we conclude the problem, as on the Smith chart, we already demonstrate that the optimal position, shunt position, is H. So you need to calculate, or you need to find out how much distance that you should travel to get to point H. So remember that you're starting from position A, which is on top of the Smith chart, and you need to move to position H, which is down below. And what is the distance between A and H? Okay, so since you have already worked on Smith chart for a couple of times, I suppose you already know that how to do this. You need to draw a straight line from the center to the outer circumference of the Smith chart and read out the distance. So for position A, the corresponding distance mark is 0.12 lambda. And the corresponding distance for H is 0.346 lambda, right? So the distance is 0.346 minus 0.125. You can do the math, right? So the distance required is 0.221 lambda. OK， 好，再提醒一下，在那个 Smith chart 最外面那一圈哈，那一个从最左边开始0，然后正上方0.125，右边0.25，这个是用什么？用波长来去表示的那个。你可以把它想象成什么？想象成高速公路上面的那个里程的那个位置的 marker 啊，所以它不是绝对值的，你要算的是它的相对值啊。比如说，建国北路是在25，然后那个国道2号，也是去机场国道2号是在51，所以你从建国北路在国道1号从建国北路到那个机场交流道是51减25等于26嘛，对不对？好，所以这一个圈圈也是帮助你去方便计算的那个里程的那个 marker 而已。好，所以在这个例子里头的话，你就是要读出 h 对应到的是 0.346 lambda 哈 ，a 对到的是 0.125， 所以它们差 0.221， 就是你在传输线上面要走的距离。哈，所以从负载的位置往左边走 0.221 个 lambda， 你就可以进到 h， 然后在 h 接 0.8a， 你就到 g， 然后后面呢，不管你怎么转，它的 SWR ratio 都是 1.35， 不然的话，你原来的 SWR ratio 是多少？大概3左右吧。哦，从这边看起来大概3左右，所以你就可以把 SWR ratio 从3降到 0.135。OK。Okay, we can also demonstrate this with the Smith chart tool. Oh, okay, so I guess I will just skip this part. And okay, that should conclude our lecture today. And on Friday, I will finish section 7.6. And for the final, the scope will cover from 7.1 to 7.6. And the final is when? Next Friday. All right. So this Friday you should hang out the homework set number 7, and on next Friday, the final day, you should hang out the homework set number 8. All right. Okay. So before we